I'll switch and move around between like Arabic and English, but I'll do my best. So Jazakallah khair everyone for coming. I'm going to keep the chat open. So if anyone has any questions, let me know, and I will try to I'll try to answer them during the slides, or just raise your hand, and I think I can also see that. Without further ado, let's get started. Bismillah. So let's see here. What's the problem that Tartil is trying to solve? Alhamdulillah, يعني بفضل رب العالمين يعني عدد المسلمين يعني around the world وصل لأكثر من 2 بليون مسلم. ونحن طبعا نعرف انه نقرا القرآن 5 مرات في اليوم من جزء من الصلوات الخمس. وغيرها يعني نقرا في منا نقرا القرآن يعني خارج اوقات الصلوات، يوم الجمعة، سورة الكهف، يعني القرآن هو جزء اساسي من حياة المسلمين. للأسف فقط 15% من العدد المسلمين بيتكلموا اللغة العربية بشكل يعني بالفصحى، وهي بتكون لغتهم الأساسية. وبنفس الوقت إجازة القرآن زالت on its own, that you have to verbally pronunciate it and recite it with the correct pronunciation, with correct tartil. And so it's important to not just memorize and understand the Quran, but to also recite it correctly. So what Tartil is trying to solve is providing the necessary tools to enable Muslims to read, to learn, and to memorize and recite the Quran with ease. We do this through different processes such as memorization mode, transcription, search, and these are some of the first features. Ideally, down the line, we want to enable things like tracking, progress, correction, inshallah. Right now, we're working internally very hard. Alhamdulillah, and fadl Rabbil Alameen, we gathered over 250,000 recordings, and I'll go over that big data set we have right now to train our new machine learning models. And inshallah, like with that, we're able to get high enough accuracy that we can perform word by word or even character by character recognition. What is the history of Tartil? I think I have one of the co-founders here as well, Abdul Latif. It started with a group of young individuals in the Bay Area who were part of a Muslim hackathon. They started out Tartil as a data collection labeling project. عادة لما بدك تبدأ في مشروع machine learning لازم يكون عندك الداتا. يعني الداتا هو يعني aside from machine learning with science behind it, the data is the rocket fuel. Regular ordinary Muslims that recite the Quran. And so if we want to train a machine learning model on Quran recitation, it needs to generalize. It can't overfit on certain data. We can't make it overfit on قراءة المحترفين. Rather, we need it to be generalized so that the general population can use it. So Tartil started out as a data collection labeling project. Alhamdulillah, once we reached around 50,000 recordings, we decided to start with and labeled recordings at that. We decided to start working with machine learning model and iteration. We began to explore partnerships with other people to discuss how we can better enhance the Tartil project. This is where we started collaboration with another project called Iqra. We went through the Mass Challenge Startup Accelerator to try and understand how we can deliver something that actually addresses the needs of the Muslims and actually support their use case, to deliver something that's not just like as a side project, but as something that's a professional feature that could be used by people everywhere. In the second half of 2019, we decided to have a launch. We had a mobile app release. We released multiple features such as memorization mode and translations on our web app. And now we've mostly been focusing on mobile app development. And alhamdulillah, in 2020, ideally we want to focus on starting those collaborations, actually making Tartil a part of the masajid you go to, the classes you might attend, the Quran classes, as well as improving on the overall machine learning model. For 2021, ideally you want to start doing transcription, translations, working with different masajid, working with different institutes, moving up to correction, word by word correction. Our goal is to have word correction by 2021, inshallah. And then focusing on some of the premium metrics and features such as tracking, profiles, groups. فمثلا انت بيكون عندك يعني حلقة قرآن مع اشخاص ثانيين, you guys can track your Quran recitation together. You can individually track what mistakes you're making. You can track the progress you've recited so far. And then ideally we want to start expanding and supporting people in different regions, مش بس في أمريكا وفي أوروبا, بس يعني كمان in Saudi Arabia, in the Middle East and North Africa region, in Asia, and addressing their specific needs. Because the way Muslims learn across these different regions is also varied. So ideally, we want to tailor the experience for that. So let's dive into the machine learning problem. عادة we think of the machine learning model as this black box. You give it an input and it gives you an output. In our case, we give it the input as speech, and we expect the output to be some sort of text, to identify some sort of text. In this black box, there's a lot of elements that go into it. And it starts with the data collection. You need to have the data to train your data set. Once you have the data, it's not enough. You need to have annotations or labels for your inputs. So once you have the data collection, you need to start to annotate it. After you have your labeled data, then you can start running your experiments. What models work? What types of architectures work best with predicting what a certain data point or input is? And so that's where you can start experimenting. And then it's followed by actual training. So you need to train the model, you need to run it, you need to try it out, deploy it, and then you need to evaluate its progress. Is it actually performing well? Is it regressing? Is it doing some weird behavior? Does it have some weird outliers, or does it overfit? So this is the whole pipeline of the machine learning model. With research, عادة في الأكاديمية لما تكون يعني شغالين في يعني within like the frames of an academic setting, most of the work is on experiments and training. Usually there's like an open source data set, or someone else has collected a data set. Usually it's rare that you need to collect your own data, since a lot of other people have worked very hard to perform data collection. But in production, most of the work focuses on deployment and evaluation. Once you deploy your machine learning model, how do you know if it's performing well? How do you know if it's actually like providing users with the right results? How do you know if it's working? And so you want to make sure that, you know, you have your machine learning model. How do you make sure it delivers the results you need for your users? So I'm going to talk a bit about the deployment and evaluation side, but I'll also touch on how we had to go through this entire process, since we were doing something from zero, from scratch. So we start out with data collection. This is the first iteration, or one of the first iterations of our website. It was very simple, very intuitive. You click a single button and you start reciting a verse. And we don't do any pre-processing. We don't do any evaluation. We just collect your data, and you know we use it as a starting point. And this is usually the first step. Usually you don't want to make things overcomplicated from the start. You want to keep things simple. Make it easy for others to actually use your data collection platform. And in order to actually collect data, we had to do marketing, demos. We even had iftar fundraisers to get people to, you know, recite for Tartil to start data collection. If you probably scroll through our Facebook history and on Tartil, you'll probably see like our fundraisers for iftar and getting people excited about Tartil and the technology. Once we've collected all the data, it's time to actually label it or to annotate it. So we drawed on the experience from Mozilla. Mozilla has a project called Open Voice, where random people, you know, they don't recite يعني زي ما نحن we recite the Quran, but they speak English or, you know, sentences, and they're evaluated, you know, by the open source community. So this is one of their simple interfaces. we kind of borrowed from, I guess, heavily from their interface, just because it was very simple, very easy to use, and it's pretty straightforward. Uh, we came across an interesting problem, which is privacy. Um, than when someone wants to recite the Quran, when a female wants to recite the Quran, usually her voice shouldn't be listened to by non-female individuals. So this came as an interesting challenge where from the get-go we already had to do some sort of machine learning or classification. So I'll go over this during the demo, but we had to build a small gender classifier so that if someone wants to listen only to male recitations or only to or male and female recitations, they could do so. And that way we did our best, given the tools we had and the circumstances, to make sure that, you know, we tried to protect the privacy as much as possible. We kept the data anonymized. Um, and we tried to enhance the evaluation experience. In this case, our evaluation was very simple. It was whether the evaluation was correct or incorrect. We didn't do word by word or, you know, timestamps of the recitation. Rather, we just said, is the recitation of the correct ayah or not? And this was actually good enough for us to reach a stage where we can do classification on the ayahs on the data set. It was only after 18 months of actually collecting the data, labeling it, and we were able to actually start training the machine learning model, and where we actually were able to start experimenting and evaluating. So this is where we actually got, after we labeled the data set, we reached, alhamdulillah, to around 75,000 recordings. We began working on the machine learning element and component of it. Initially, we were looking at OpenNMT, which is a similar RNN. It's used for speech. OpenNMT is a model used for speech, but we realized that RNNs, um, they're great. They're great architectures for analyzing sequential data, such as time series data protection. And so in theory, they're also able to handle long-term dependencies. If you were to recite a partial verse, usually you don't have enough context on what that means. If I say yeah, you don't know if it's na ma noon or ya ma ya. So it's difficult to understand what someone is reciting. But when you say ya ayyuhalladhina amanu, you have the whole context of the audio to understand that what was recited before is most likely ya with a ya. In English, this could be an example of B. Do you know if you said the word B as in boy or V as in vendetta? Um, and so this is what the RNN architecture tries to solve. In practice, RNNs don't really, you know, they don't actually work that well in practice. So we introduce something called a long short-term memory network, which is a special type of RNN. And this is capable of handling long-term dependencies. LSTMs are basically units of a RNN, and the LSTM is composed of a cell with an input gate, an output gate, and a forget gate. I won't dive too much into the technical details, but we'll go over that shortly. So this is the architecture of a LSTM. This right here is a simple RNN. Basically, you have your input, and then you have some predicted output, and then you keep looping over the same cell over and over again. But if you unroll this out, basically, for every input, you get a prediction, and based on the prediction, you have a state based on the previous predictions. And so this is how you maintain your long-term dependency. So if you recite, let's say, a syllable here, if you say yeah in this and as this input, you get an expected prediction, but then that is also fed to the next layer. And so if I say here ayyuha, most likely this prediction is going to change, and it's going to think I'm saying yeah ayyuha, and then it keeps on going all the way to the end. And this is how we keep the state, we keep the cell state over time until we get the final prediction. Deep inside, this is how the LSTM actually works. So there's two basically components of this. One is the cell state. So the cell state basically takes whatever you got previously and moves it over from one cell to the other. And so this cell state doesn't change. It's modified just by the forget gate and the input gate. And I'll get into those in 2 minutes. So this cell state is consistent across all units, all LSTM units. For the forget gate basically decides whether we should forget the state or we should keep it. So sometimes you change your context, or you recite a completely different sentence. The forget gate determines whether you should reset your cell state or whether you should maintain it and maintain context of the previous recitation or the previous prediction. The input gate basically decides is what augments the cell state. So you have your input, and when you want to augment the cell state, you want to update the cell state. This is what the input gate does. It basically updates your cell state. The output gate is where you actually perform your prediction and where you output what the result is. And all of these are basically sigmoids. I won't dive too deep into the details, but then and they're very simple, like hyperbolic tan operations. So they're not really complicated mathematical operations, but they're performed in large sequences. And so this is why you need something like a GPU, as always, like a GPU to train your model. It's just very simple mathematical operations, but performed over a very large scale. Is there any questions? I hope I'm not going too fast. Clear. Sounds good. So with our data set, our data set is unique in the sense that we also have tajweed. ففي القرآن عندك المد والإدغام والإخفاء, and all of these rules basically result in special characteristics or behaviors in the data set. If I recite a word, I'm most likely not just going to recite the word by itself, but I'm also going to do some med. So if I say يا أيها الذين آمنوا, I'm doing a med, or قل يا أيها الكافرون لا أعبد ما تعبدون. And so these different syllables, when you have multiple syllables, usually this results in repetition of the word. So how do we handle identifying these basically the med and the tajweed? We use something called CTC decoding, or I keep forgetting this, connectionist temporal classification decoding. Basically what this does, if you have a series of what's called tokens or predictions, you drop the repeats and you drop the spaces, or like the gaps in the audio. So they give an example here. You say hello world, but with repeats. What CTC does is basically it's able to predict when repeats occur to give you a final clean output. How does this work? So assuming you have some input X and a labeled output Y, you want to find the probability that the output is Y given some input X. So we're given some input, and given we have like these two inputs, for example, two E's, and we know the label is actually just one E. What's the probability that, what CTC does is it tries to find this probability, and it sums it over the probability of every single alignment step by step. Now this is obviously going to be very costly. If you perform this probability prediction on every single character, for every single sentence, over entire label, the prediction is going to be very costly. So what we do is some form of dynamic programming. So essentially what happens is anything that is similar or aligned, or any alignments that are similar, are basically merged. And this way, it minimizes the number of computations that need to be performed. So one question that came up, if you want to do tajweed evaluation, repeats are important, right? Yes, they are important, but what you want to identify is the source, the ground truth text. فمثلا لو حركة المد, if your data set was labeled with حركة المد, you're able to know that this the audio associated with this character is a med and not just multiple alifs. So what do I mean by this? I think the best, if I should have given a better Arabic example here, but essentially if you're saying ya ayyuha, ya is only two words, two characters, sorry, and you only want to recognize those two characters. However, we train our data with tashkil, and so what this does is we're able to differentiate between the occurrence of an alif on its own versus the occurrence of a med. So, for example, if I train when I train my model on labeled data with tashkil, it can differentiate between when a regular alif or a regular ya is recited versus when one is recited with med or with a certain tajweed. So yeah, I hope that answers the question. So after we go through all of this, so we've collected our data, we've annotated it, we've identified, a good architecture and our machine learning model and architecture to train our data on. The next step is to actually deploy this, to actually deploy it so that people can use it. So this is where the deployment works. Our first iteration of the deployment was very simple. And like I said before, you want to keep things simple. So keep it simple, stupid. In fact, I think I have a picture of our very first server, essentially. This is, I basically put this together. I bought a small GPU, we bought a small rack, put the small Wi-Fi card on it. I hope you guys can all see my screen. And basically we just used this to log in. We didn't have AWS, we didn't have cloud, we didn't have none of that stuff. We just ran it on a single GPU, and we tried things out initially via this server. So this was the start. Once we understood how the basics work, how deployment works, how training works, that's when we started to grow. It's like, okay, now we need to scale, now we need to support other people. So this is our first iteration of the deployment pipeline. All the deployment is built on AWS. It's broken into 3 steps. The first step is pre-processing data. So you need to process the data. Usually you have raw data. You need to change the sampling rate. You need to clean it up. You need to remove distortions, noise, whatever it is, and augment it. And then the next step is actually training. So then this is where we perform training, followed by deployment, and then having a voice server. So we have an Amazon RDS, which is basically a database. So all our audio recordings are stored in our database. We manually pull recordings from our database and evaluate them. And then we process them, we augment them. Sometimes we need to change the sampling rate, the bit rate. When we're dealing with audio data, we need to clean up empty audio recordings. We need to clean up data that's incorrect or remove those. So all of that, we did it manually. We just pulled from the database locally. We evaluated the audio, we augmented it locally. And then we have a cloud instance that runs training. So we kick off a training job manually as well. And then we deploy it using a SageMaker endpoint. Excuse me. So we deploy using AWS SageMaker, and then we have an auto-scaling group. Basically what this does is it balances out the load. So as more people use your application, instead of them hitting like one server, you're able to scale essentially, and you're able to scale across multiple servers. I think during Ramadan was the first time where we had to use auto scaling. Previously, we only had one basically instance running our voice server. now we have like 5 different instances, and we're scaling up to 7, each of them serving traffic for many people. So yeah, so this basically, the server scales up to multiple servers so that we can handle the load and we can handle the traffic. For those of you who are familiar with AWS, we also use Elastic Beanstalk. So this voice server is deployed using Elastic Beanstalk, and this is what we use to communicate with our users and deliver results. So this is the first iteration. The next iteration, and what we're currently working on now, is automating the pre-processing section. So you'll notice training is the same, and the way we communicate with our users is the same. But instead of us manually pulling from the database, instead we perform what's called an extract, transform, load workflow. For those of you that are familiar with data science, ETL, you probably know what ETL is, but extract, transform, load is basically taking data from some source, transforming it so that it fits your needs, and then loading it into some new database that is suitable for, maybe a specific training job or process. So instead, what we want to do is when we get recordings in our database, we automatically want to perform this ETL workflow. So we clean up the data, we augment it, we load it, we make sure it's ready, and then we put it into its own database. So one database might have recordings that are a certain sampling rate, or recordings that are only of Surah Al-Alaq, or maybe of Ayatul Dayn. Maybe we only want recordings of Ayatul Dayn. So we just put them into these separate databases so that we have them ready for processing. And then we just perform the same training workflow where we train the model, we deploy it, and then the users are able to access it. Now, the next step, so this is what we're currently working on. Ideally, the next step, oh, and one thing I forgot. What's nice about this whole workflow is we have a data network. Whenever someone recites data or recites audio, we automatically can identify what surah they're reciting and pull that up and put it back into our database. So we have this whole workflow, which is basically our own data network. So the more that people use our application, the more data we collect, the better our machine learning model performs. So it's a nice feedback loop of collecting audio recordings. I'll pause here just to make sure there's no questions. Do you confirm that the ML model returned the correct data from the feedback loop from the user? So what we do is we identify what surah or ayah the person recited, and based on that, we perform a segmentation. So let's say we identified, we have our own deterministic search algorithm. So if someone recites a certain verse or audio, we transform it to text, and then we try to identify what that verse is, and that's what you see right now when you use our mobile app. If you're reciting a verse, when we basically segment that audio and we deploy back to our database, we do a second round of confirmations. So as part of this ETL workflow, we also use Google Speech to make sure that the recitation is in fact what it was labeled. So we basically do 2 double checks. The first check is essentially what happens in the voice server, and the second check occurs in the ETL workflow. So that makes sure that the recitation is actually what it is, and this is all an automated process. So we actually make sure we do our best to automate as much of this. So this goes back to, yes, garbage in, garbage out. How do you keep your data set clean and high quality? This is how we're trying. So this is why we try to automate the process. But ideally, what we want to have is for those recordings that don't meet a certain threshold or that aren't labeled, ideally we want to manually evaluate them, and that's part of another process we want to work on. Do you need to keep in mind the different qira'at of Quran and training? Yes. Right now, we make an assumption that all the qira'at are in hafs, and we ask, especially people who contribute the recordings, that their qira'ah is in hafs, and if not, they specify their qira'ah. Ideally, we want to expand this into having different models trained on different qira'at, so some for hafs, some for warsh, and then focus on those related to those from different ethnicities. So, for example, someone from Saudi might not have the same pronunciation or recitation as someone from Malaysia or someone from America. So ideally, we want to have different demographics for different models for each different demographic or different qira'at. But that's essentially future work. Right now, we're just focusing on hafs. Can you talk about the augmentation step? So yes, I actually just realized I didn't put the slides for augmentation, but basically we perform artificial augmentation of the data. So we add artificial noise such as one augmentation we do is basically time overlap. So we overlap some of the audio from a previous ayah and the next ayah, so that there's just a slight overlap, so the machine learning model knows how to what the next ayah usually will be. And then another augmentation we do is time shifting. So we do some time scaling on the verse. We also do some frequency shifting and manipulation. So we do play around with the frequency of the audio recording to include different noise. So those are some of the augmentations we perform. So we artificially expand the data set. So the next iteration of our deployment pipeline, instead of playing around with the pre-processing, the next step is to work more on training. So like I said before, training occurs manually, so we have to manually kick off a job. So assuming we get all the process data, the next step is basically to run training on Docker containers. The reason you want to use containers in general is just because it's reproducible. It makes it easy to keep your workflow consistent and in a stable state. So basically, we can scale out multiple containers. Each one of them performs a certain training job, and they perform different experiments. So we use different hyperparameters, different optimizations that we can experiment with and identify which one results in the best performing model, as well as training different models. So example, training models on data sets that are specifically for qira'at hafs or qira'at warsh, or from those from a certain demographic. So ideally, this is why we want to switch to container-based workloads, and then that performs all the training. And then what we can also do is we can have model checkpoints. So as you know, model training is expensive and it takes time. You don't want to lose all your data. So what you do is you checkpoint your model at certain stages to make sure you can continue training, or you can do like transfer learning after your model has calculated all its weights or hyperparameters. So we want to make sure we store our checkpoints somewhere that we can use them for future reference to compare with different models, see which one performs the best. And then we have the same deployment as before. We have our auto-scaling group, which in our inference, so the model is deployed to SageMaker inference, and then the voice server serves all those results to users. So yeah, one question that came up: will your data be open source? Eventually, yes, we do plan on making certain subsets of our data open source. We started out with the first 25K recordings, followed by the V2 data set, I believe is live also with 50K labeled recordings. Ideally, we want to start in basically promoting people to try out machine learning problems and try to improve the state of the art. The reason we haven't open sourced the entire data set is basically we're very limited on like engineering bandwidth, and there's a lot of pre-processing that needs to be done in order to deliver an actually clean data set. So we do need to perform that pre-processing and prepare that data for you before it can be consumed. So we only processed for external use 50K recordings. We still have, right now it's blown up to 250K recordings. So we need to process that recordings before we can deliver it. But at the same time, we want to make sure that we respect people's privacy. We make sure that the data has only like fair use. So it's used by like trusted individuals or institutions. Kind of similar to what Mozilla does. They have their open source data set, but they keep it anonymized, they keep it private, and they keep it labeled so that it's actually usable by people. So the last step in this whole process is evaluation. So we went through collection, annotation, experimentation. So we played around with different models, starting with OpenNMT, and then we settled on DeepSpeech, and then now we deployed it, and so now we need to evaluate, is our model actually performing well? So with evaluation, obviously you want to automate this process, but for now we're basically using simple Excel sheets. We take the result of one model, we put it in an Excel sheet, we average it over like a validation set. So obviously we do the standard, train, test, validation split when training a machine learning model. Ideally, though, this would be automated. However, this is an example of one of our more recent training sets. So we performed, we evaluated around 50K audio recordings, and we augmented them as well. And so far, we reached about 92% word error rate on around 50K files plus augmentations. And alhamdulillah, this is pretty good. So the next step is basically running this on 250,000 files, as well as automating the evaluation workflow and making sure that we get consistent results for evaluations. Okay, now's the time for the demo. Let's see here. So I hope everyone can see my screen. Looks like I'm still screen sharing, so yes. So we host a public repository for pre-processing and training the Tartil dataset, as well as some examples of certain experiments we've done. So the way it works, the README basically explains what you need to do in order to get it working. But essentially, we provide 4 important utilities. The first is the download utility. So you can use this to download the data set locally to your the V1 data set, that is, locally to your machine. Then you can create your train test split. So this creates a CSV file of all the audio recordings split into 3 different sections: one for training, one for testing, and one for validation. As you probably should know, model training occurs on the training data set. The test set is left just to make sure the model is improving, and then the validation set is basically the keep out data set. The model never sees the validation set until the end, and so it's never really trained on it. So it's basically completely new data, and that actually is the best way to evaluate the performance of your model in the wild. So yeah. Then what's nice about DeepSpeech is that usually it can use the alphabet or vocabulary to improve the performance of the model. So we have example scripts for creating CSV files that make it easy to get started on training on Mozilla's DeepSpeech, or any implementation of DeepSpeech for that matter. We also have different essentially Jupyter notebooks that explain some of the work we've done earlier. For example, we have scripts that compare different models. More recently, we compare like Google Speech with our implementation of DeepSpeech, or our implementation of the model, as well as other models. We have example interfaces from one of our collaborators called Gradio. Gradio basically helped us with data augmentation, labeling, and annotation. And so what they do is they generate augmentations and interfaces to quickly test and try out your machine learning model, as well as some training notebooks. So for example, we have a gender classification model notebook, as well as a sequence-to-sequence model. So this is one of our first experiments with sequence-to-sequence architecture. So these Jupyter notebooks go over essentially like how to read, load the data set, and train your ML model, as well as the results. So you'll notice, for example, for gender classification, we performed like some initial results on I think it was 5,000 recordings, and we were able to classify, with approximately 60% accuracy, what the gender of someone is. And this is obviously one of our first iterations. So there's obviously more. If once we add more data, you can actually try this out on your own, and see how we actually perform all of this. Here's an example of a sequence-to-sequence model. One thing we did initially is generate one-hot encodings of the data. So rather than labeling the data or waiting for the data to be labeled manually back in the early days, we generated one-hot encodings for the data set. And so that made it a really easy way of just quickly experimenting and trying out different architectures, and understanding what the best architecture could be, or to use for our data set. So yeah, this is another example of a sequence-to-sequence model. So we provide the loss curves, we provide the way, how do you perform inference. I think this is one of the initial experiments where the model was just learning Allahu, and I think that was because we just trained this on Surah Al-Fatiha. So all it could learn from Surah Al-Fatiha was basically Allahu. So you can see like the initial results and how we progressed to date. Lastly, here's an example of a Gradio interface. So this Gradio interface basically makes it easy for you to try out a model deployment. So it starts a local server, and you can basically drag and drop audio files, so you can see what the prediction of a model is from your Jupyter notebook. So it's a really nice way of testing out how your model is performing. Any questions here so far? I know we're a bit over time, so I want to leave some time for like Q&A and some questions. Okay. If there are no questions, how to participate? In the sense that how to be part of Tartil, or like how to start training. For Tartil, I think we're definitely looking for talented engineers. We definitely need help. So probably the best way is essentially just sending me your resume, and I'll have my contacts in the slide after. But you can also basically participate with the open source data set we have. Data set, splitting it up and generating the CSV file. And then all you need to do is basically take that, try it out on your own recitation, and essentially, your own model, and try it out on like your own recitations, for example, and work from there. Yeah, wave to letter for this test. Yes, that's a very good question. I think when wave to letter came out, or when we heard about it, we were already in the process of using DeepSpeech. However, it's definitely on our roadmap to evaluate wave to letter. My understanding was it was much easier to use, and it is more straightforward. Like, it's more accurate, to the best of my understanding. Plus, it's more flexible. So they provide a lot of modules that make it easy for you to plug and play different different components or different units of the architecture. So no, we haven't evaluated, but definitely the next step is to work on wave to letter, inshallah. Yeah.